Special thanks goes to our gold sponsor, Accenture.
Thanks for the introduction. I'm really happy to be here. And I have to start my talk with an apology. I apologize for a really misleading title. Well, not really misleading, but it says that it's about building native Node.js add-ons in Reason. But unfortunately, most of the examples are going to be in OCaml. But I hope it's not a big deal. It's kind of the same thing. Indeed, I've been involved with Flow for quite some time. And it was my sort of gateway drug to OCaml development. But before that, I was a Node.js developer and minor Node.js core contributor. So in this talk, I wanted to marry these two things and talk about building Node.js add-ons in Reason or OCaml, whatever you like. It's going to work either way. So first of all, what are Node.js add-ons? I don't really expect a lot of you to have experience with writing Node.js add-ons. Even if you are a full-time Node.js developer, you probably have never had a situation where you needed to do so. Because most of the things you can do in pure JavaScript, or you can just grab a package from NPM, and you're done. But you have definitely used one directly or indirectly. For example, I don't know whether you can see this. If you install a fresh Create React app, that's what you get inside. Like, there is a bunch of .node files. And these .node files are Node.js add-ons. Why would you want to do this? Why would you want to write Node.js add-on? Well, there are a few reasons for this. First of all, you want to use language features that are absent in JavaScript. And, well, there are many features absent in JavaScript. For example, static typing or multi-threading, or the main feature that is really absent in JavaScript, and now why people choose to write Node.js add-ons, is performance. When you want to get the most of your server, that's what you're going to do. That's what you're going to try. You're going to try to write some small piece of code in C++ and have a significant performance boost. Another reason is access to the ecosystem. And make no mistake, C and C++ ecosystem is really old and really vast. So if you want something that doesn't exist in the JavaScript world, yeah, it probably exists in C or C++ world, and it's really high quality and really performant. So oftentimes when you want to access a database, or you want to encode or decode some sort of binary format, you probably find a C++ library for that is performant, production ready, and it is already there. And rewriting the same code in JavaScript, it's going to take a lot of time. It's going to be error-prone and less performant. And the last reason is access to the platform, and it is exactly what happened in the Create React app example. The only native add-on there is fast events, and it's basically a tiny module that is used to access a fast events API on macOS. It is a native platform API that is only available in C. So if you want something like this, well, there is not much you can do. You have to write an add-on. What's inside this file? It kind of looks like this. Like, you probably don't want to open it in your terminal or text editor, because it's binary. And in this particular case, it is a macro file, which is a macOS binary format. And it's basically what is called a shared object or dynamically loaded library. So if you ever saw one of these, Node.js add-ons are essentially the same. The only difference is that they use .node add-on, .node extension, in order to show that they're really not going to work with any other runtime, with any other process. Because if a process tries to load such a shared object, it's not going to have all the necessary symbols that this add-on depends on. It basically works like this, the initialization process. Node.js runtime process, it DL opens the add-on, loads it, and it expects the add-on to call a single function, node model register. And after that, it is all done, and add-on can do whatever it wants to do. How do you build an add-on, like the old way, not the one that I'm going to present today? Like the first way is, the standard way is to use V8 API, which is a C++ API. For a long time, it was like the only way or the main way. But due to constant breaking changes in V8 API, it very quickly became a mess, and people understood that they can't really deal with this mess of C macros and weird wrappers. And you really had to do this if you wanted to support multiple Node.js versions. And they came up with none, which is also C++. None stands for native abstractions for Node. And it basically is a collection of macros and wrappers that help you to build Node.js add-ons in a backwards compatible and forwards compatible way. So the idea is that they provide a really consistent API. But API is not enough. One problem with using this approach is that sometimes when you upgrade, not all the times, but sometimes when you upgrade Node.js version, you have to recompile your add-ons. And even if you don't really have to change a line of code, you still have to recompile it. And this is because while none provides API compatibility, it doesn't do much in terms of ABI compatibility or application binary interface compatibility. So you're forced to do that. To solve this problem, Node.js came up with an API. It is like the newest one, and it is a C API. It was introduced in Node 8, I think, and it is just became available as a stable API in a Node 10. So basically, the idea is that if you build your add-on on top of an API, then you don't have to recompile your add-ons, like ever, unless there is explicit breaking change in that API or ABI. Let's see how you would do that the old way. Like, first of all, to build an add-on, you need a file that is called binds.in.zip. It's basically metadata for the build system that is called zip. Yeah. It actually is it's really good and interesting system, and you can call it a meta build system. Basically, zip stands for generate your projects. What it does, it generates make files or Xcode projects, Visual Studio projects, and etc. And it is used in Node because it is used in V8, and it is used in V8 because it is used in Chrome. So that's the story there. Next, what you need is add-on itself. It's a C++ file. Don't really try to understand what's going on. I just wanted to show that it is a mess. It is ugly. It is unsafe. It is C++. So yeah, that's what you have to do the old way. And when you have this, you run node.zip, and you get the add-on. The add-on is a .node file, and you can require it just like any other file, like .js file, works the same. Okay, so it's not good, and we obviously want to write code in OCaml or Reason, because that's why we're here. And today I want to show you something that I call OCaml Node, and it is really new and really unstable, and etc. So work in progress, basically. But still, what I want to do is I want to explain a bit how it works and dive into live coding. And it's probably going to end badly, and I'm going to embarrass myself. but that's the fun, I guess. So a camel node, it's built using C and a camel. It uses an API, that's a new API, which is it's really nice because OCaml's native API is C as well. So I didn't have to go through the hassle of using C++ and C, trying to merge C++ and C. It's not that easy. It uses JBuilder to build OCaml or Dune. I'm not sure whether it's the right name. And Easy, which is, if you don't know, it's a really great tool, which is designed to provide an NPM-like experience for a native OCaml development. Not really just OCaml development, but primarily. And it is used to download packages, and it manages the whole environment. Basically, you don't have to care about installing anything, installing OCaml compiler or OPAM or Merlin or anything. It's going to install everything for you. I'm going to show that, how it works. That's kind of how the build system works. There are a lot of levels. Basically, it starts with NPM, because when you're going to install your package from the NPM, it's calling OCaml node, which is just a tiny script that does two things, and one of them it calls easy build. And easy works with JBuilder. It runs JBuilder in a configured sandbox. And from there, OCaml compiler is called, and Node.js is called in order to build like the core of the plugin. That's, I don't know whether it's interesting or not. I'm going to show it a bit later. So I guess it's the demo time. So first of all, let's create a fresh add-on, a really fresh one. It's basically an NPM package. So we can call NPM init. It won't do much for us at this point, but it's nice to have it there. Like the next thing that we want to do is we want to initialize this package using OCaml node. It's one of the two commands, like OCaml node init. What it's doing is it generates a bunch of files for us, which I'm going to show, and then it runs as install, and then it runs as build. That's how easy it works. It's amazing. Not really everything is cached, but still. Okay, so we are done. So unfortunately, we're going to have to open two windows. One is for the outer layer, and one is for the source folder. When we do this, plugin integration with Easy kicks in, and it's actually able to detect that we are using Easy and that we're using a specific Merlin version installed, and it is supposed to just work. So let me see whether it works. Yeah, it works out of the box. So this is an example of a simple add-on that adds numbers, but we're going to start with something a bit easier. We're going to remove this and start with node register. It's the first thing that you have to do in your add-on. You have to register. You do this by calling a register function, and you need to provide your exports. The simplest way to do this is just to return original exports. It kind of works like in Node.js. When you're inside of a module, there is an exports object configured. You can just add stuff to this object, or you can override it completely. So let's try to compile it and try to run it. As I already mentioned, you can require Node.js addons like they were usual files. And that's what we're going to do. The build addon is located here. Build default addon.node. Okay. So it is supposed to be just an empty object. Let's see. So we have to rebuild the whole thing. It's done. So the easiest thing we can do to play with this setup is we can return something else instead of this object. Let's try this. Let's try returning a number. And in order to make a number, we use a value module, which has a bunch of functions to work with primitive types, such as integers, floats, booleans, strings, etc. So we have to write value of float. That's it. Okay, this is good. But you're probably not going to do this or anything like this in real environments. What you want to do is you want to keep the original object and add fields to that object. This is one of the core ideas of a common node. Basically, we have to deal with the hierarchy of values. In V8, they are modeled as classes with inheritance. But we don't really want to do this in a camel, and we want to avoid classes as much as possible, although they are there. So in order to achieve the same result, what we can do is we can use abstract types. How it works? Basically, our core type is called value T type. And we have some descendants. But what it means is that under the hood, they are actually represented by the same underlying type. And you have a bunch of functions that allow you to convert between these types. For example, we have a value T here. But in order to add fields to this object, we actually need an object T. This kind of works like this. We open the object module, and it has a function of value. There are two options for all such functions, of value or of value exception, which means exception. So the first one, it returns option. The second one, it raises an exception where something goes wrong. Well, in this particular case, we don't really want to deal with option because we know for a fact that it's going to be an object. So we can just do this. So, right, so now we have an object. And once we're done, we want to convert it back in order to return it. So we are going to call to object, or to value. Right, so this does nothing. But in between, we have access to the object, and we can mess with it. Like let's set a field. Let's see. So we need this field value, and we need a type. We need a value T, for example, a number or a float to be specific. And the last argument is actually an object, so pipeline works. And that's that. All right. Probably what you want to do, like right off the bat, is to make functions. And original example actually had a function that adds two numbers. And I think now we can get back to that example. A function is represented, not represented. In order to create a function, in order to create a Node.js function or JavaScript function, you need to provide an camel function that takes a list of values and returns a single value. So let's do that. that's arguments is going to be a list of values. First of all, we need to make sure that we have two. We have just two, and that is easy to do with pattern matching. Okay, let's say we want the first two items of the list. If there are more, we don't care about them. And otherwise, we'll just raise an error. Okay. So let's take a look at what A and B are. No, we can't because we don't really know what args are. Okay. That's the problem with type inference. Like, yeah, you have to write the code first in order to know what the types are. Okay. So we really want them to be floats. So we could do something like this in the end. Well, this doesn't really, oh, yeah. Oh, it actually does work, which is weird. Okay, this is actually not going to work once we set this function. So to create a JavaScript function, we call in function make and provide this sum. So this is an error, and here is a simple explanation. What we need is a function that takes value list, and that is not value list. This is going to be a float list. So if A and B are values, we really need to convert them using value to float. We are going to choose the version with the exception because we don't really care about safety. Okay, to float. Okay, so something else is wrong. Okay. Oh, okay. So that's what I already talked about. Function make, it returns a value of type of function t. Under the hood, it is the same as value t, but it is an extra type. So at this point, type system doesn't know that it's the same thing, and we need to actually call function to value. Okay, so that's it. And let's modify our JavaScript file. Okay, that's not right. Addon foo. Works. So yeah, thank you. You probably wonder what's the deal with exceptions. Like, why would you do that? How you can use this unsafe functions? They're supposed to be unsafe, right? They throw exceptions and nobody is catching them. But at the same time, what would you do if you were trying to implement such a function and you were given a wrong value? You probably would throw an error. And let's see what would happen if we do that. For example, let's make it a string. Type error. So that's probably what would you do by hand. Or maybe just one argument. Not enough args, but that's what we've written here. So it's basically fine to do that. But still, this code doesn't really look good, well, in my opinion, because there is a lot of boilerplate. One thing that we can do is, like an easy one, I actually made a simple alias in order to remove this wrapper here, but I mean, it doesn't give much. And here what magic is. Now I'm going to show something that is called, that I call signatures. First of all, we need to construct a signature that corresponds to the signature of our function or intended signature. Like in this particular case, the signature is float, float, float. In order to construct it, you use a model that is called signature. And that's our signature. Let's take a look at this type. The type is float, 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 not signature T, whatever that means. Oh, you're going to see. And then what we need to do, actually don't need it here. Then what we are going to do is we are going to construct a function using this signature in a very different way. There is a special function for that. It's called signature wrap. The first argument is the signature itself. And the last argument is a function. And what this function is going to be. I guess something is wrong, but yeah. Oh, okay, so what's wrong here is that signature wrap actually returns a function. No need to call function. Oh, yeah, also there is no binding there. Signature function. Still not right. Okay, let me see. Oh, yeah. Okay, this should really be fine. I'm going to fix it now because it's really worth it. So let's start from scratch. Function is going to be signature wrap. No, it's not right. I'm not sure what's going on. But that's exactly what kind of embarrassment I was talking about. I guess I have to look it up. I have it on me. No. Okay, this is a bit more involved, but still. Jesus. Okay, so we I'm going to change this part. Okay, I have no idea what happened. I could swear that I wrote the same thing. So, what happened here? First of all, we specified the signature using this weird syntax. And then, magically, we had to just provide a function that does exactly what we want, and nothing more. That's just that it works. It's obvious. It doesn't, because it's renamed. Yeah. Thank you. It works. Yeah. That's not it. Yeah. So let's take a look at how this works, because it's really interesting, and this is something that you can use in really different tasks. I just need to open another file really quick. Okay, so here is the interface of the signature module. And first of all, we need to take a look at what a codec is. A codec is a value that helps you to decode or encode a value of a specific type from your value t. And this type can be really anything. For example, you can say that, well, I'm going to take a number from this JavaScript number. Well, that's a simple one. But at the same time, you might want to take a string from this JavaScript number for some reason. And it doesn't matter here. So it's pretty abstract. You provide a decode function and encode function, and then it is created for you. And you really have a bunch of them here provided for you. And these magic operators to combine them into a signature. But what's really interesting is what's under the hood. And this is really the words that you probably need to know, at least to look it up when you have time. But you probably have heard it. The word is GADT, or Generalized Algebraic Data Types. What it looks like is like this. I'm not really going to go into any detail here because, well, honestly, I don't really know how it works. Like, it's magic. But what you know is when it compiles, it probably does what you want. So it consists of two variants, ret and cons. Cons represents arguments, and ret represents return value. So it is supposed to be like the last one. So basically, this structure forms a list or homogeneous list of values where the last value is guaranteed to represent the return type of your function. And here how the operators are defined, with nothing more than wrappers for this. And I choose them randomly, but kind of looks nice. And the only requirement for the choice of the operator is that it should be a right associative in this particular case. And then the function that really does all the magic is an Ply function. And as it is usually the case with JDTs, you have to annotate it because type inference doesn't provide the necessary result. So what it does, it takes your signature and takes a list of values and recursively applies the value one by one until it is the final one. And in the end, we know that the result is going to be correspondent to the return results of your signature. Well, that's as deep as I'm going to get into this. But instead, I'm going to show you a lot of other stuff that you could do using this mechanism. for example, first thing is, which is quite interesting, what happens when you don't really need, let's check out what happens when you provide incorrect values, because it's important, or not enough values. More arguments expected, so which is nice. The same way actually with your own type. That's a typo. Okay, but let's say that we want to handle this somehow. For example, we want this to work, something like this. Let's make it a bit different. Let's try a different codec, or a string codec, to be specific. It works exactly like this. Use the word string, and it's just the name of the binding of this codec in the signature module. And suddenly it's an error because, well, it's an operator that works on floats, and we want something like this instead. And actually, you don't even need a function here. Like, what you can do is you can use an operator directly because it is a function. And let's try it. Okay, that's. Yep. Thank you. You're very attentive. Okay. Works. Great. The next thing that we want to figure out. Okay, so obviously when there is no second value, it's going to be an error. But what if we want to do something else instead? Well, the first option. Well, not the first option. It's really the best option is to use something that is called with default. You can call this like something like a higher order codec, which basically is a function that returns, it takes a codec as an argument and returns another codec. So it sort of decorates the original codec with additional functionality. In this particular case, what it's supposed to do is it's supposed to handle the case when there is no value, and we just want the default. This works. Magic. Okay. So let me show you a couple of more codecs before moving on. So first of all, you don't really have to decode the value completely. For example, you can say that first argument is definitely a string, but the second one is a value, which is basically a no-op codec. Like what we get here is in this signature that the first argument is a string and the second one is value t, so you can do anything you want. And how could you do that? Well, there is a special function for this, which is called, unsurprisingly, typeof. What it does, it returns something called type t, which actually is a polymorphic variant. So, for example, what you could do is handle a string, and well, like we know here we know that value is a string. So, but we still don't have the string itself. So we have to call value to string x. There's no other way here, and it's going to be And here we can see that the compiler doesn't allow us to leave it just like that, because we actually need to handle all of the options. But let's say we want to do something else for number. going to be yeah, just some other string, like a number, and for everything else, we're going to say it's else. Okay, so now we have a string. Instead of this value t, we can have a string here, and still do the same. Like, you can cut them, right? So the first one is going to work exactly like this. No. Right. So let's try number. And now it shows it's a number. And now we can try anything else. That's it. Now I have to move on to another really interesting feature, and not only a feature of a camel node, but a feature of camel itself that you probably are going to love as well. One thing that you usually have to do when you write a binding for a virtual machine, like JavaScript virtual machine, you want to take your native value, like a camel value in this particular case, and attach it to a JavaScript value. But it's not going to be accessible from there. It can only be accessed from a camel code. And it's usually called external. It's called external here as well. But the question is, how do you implement this in a type-safe manner? In C or C++ APIs, they usually use void pointer. It's like a pointer to anything. And then you can cast it to anything you want. And it's basically as unsafe as it gets. And it's really not acceptable for us. So in order to do this, we use a feature of a camel that is called extensible variants. It works something like this. Let's say we want to have a type that we're going to use. And it's just a variant. And what we want is we want to convert this variant to string, but in JavaScript. So first of all, let's write the converter itself. So the next thing is that we need to write a constructor for both variants. We're going to use the same API as here. So the constructor for A, it has signature of units. It's called ext, which is external. And yeah, so how do we explain that? That this is going to be an external. The syntax is the following. We have this external type as Node.js, and this is an extensible variant. So what we do is we write type Node.js plus equals my external, for example, and is going to wrap this value of type t. And the implementation is simple. There is a unit here, and my external A, right? Something doesn't Okay, so we have the first one. Now let's make the second one for B. And in order to expose them, we use also same stuff. And now we need to expose that to string function. So let's do the same. The signature is obviously ext string. And the implementation is as follows. So we have this ext right here, and the thing is that we didn't really know that it's going to be our ext. So it can be any of the potential externals from other modules. So we need to use pattern matching to match against our constructor. External of no. Okay, and we need to provide the default, and like the only thing that we can do here is we can erase the type error. Okay, so that is pretty much it, and let's expose it as well. Okay, so now let's write JavaScript. Okay, so first of all, we can construct A and then see what the type is. And now let's do the same with B. That is bad. Or not? No, it's not. It's not really bad. Yeah, yeah. It's not. It's not bad at all. It's fine. So, if you don't see it, it's exactly what we are supposed to see. Like we construct A and get a type of A. Okay. So I don't really know whether I have more time. No? Not really. Okay. That's probably for the best, because there is a lot of this. Yeah. So you probably wonder what is the caveat? Why wouldn't? What are the cons of using this? And I already said that it's pretty much work in progress. It's probably leaks memory like a lot. But the thing is, yeah, I won't lie to you. But the problem is that in order to make this safe, we really had to affect performance a lot. The way it works in C++, when a function that implements JavaScript function is run, a special scope is created, and all the local values are attached to the scope. And when the function exits, we delete the whole scope, and it is not tied to garbage collector anymore, basically. And that's something that we can't do in OCaml, because we really want it to be safe, and we have no way of knowing whether the values from these functions are going to leak to the outside world. So we have to create a persistent reference for each and every value that we have, and it is really costly in terms of performance. The other problem is a bit more vague, and I definitely don't have time for this. Okay, so I think it was fun. At least I hope so. If you have any questions, I'll be happy to answer them. I think I'm done.